All right, so blank. All right. So all right, if I have, all right, so theta, there's cosine, sort of. It's not a great drawing, but it's cosine. And then there's sine, like that, okay? The way that, you know, to get from sine to cosine, so if this guy is sine, and this guy is cosine, way that I look at this, you can go, there's trig identities you can look up that'll tell you how you convert from a sine to an equivalent cosine. If I look at this, what I say is, if I had cosine and if I pulled cosine that direction, what's that, to the right, if I pulled him to the right, he would become sine, right? In other words, if I pulled his peak from where it is at 0 to here, it would become sine. So how far would I have to pull cosine to the right to turn it into sine?
Half a period?
Not half a period, right?
The whole period.
Not the whole period. Certainly not a whole
A
period.
quarter.
A quarter of a period.
Okay.
Right? I got to pull this peak to where that peak is. So that tells me a quarter of a period is how many degrees?
90.
90, right? So that tells me that sine of theta is equal to cosine of theta minus 90 degrees, okay? If I have a negative sign, that means that I'm shifting something to the right. I'm making it happen later in time. If I have a plus sign, then I shift it the other direction. So I think of it that way, right? I can easily kind of derive that relationship by just looking at the picture. Does that make sense?
Yeah.
So your question probably is, okay, well, what happens if I had sine of theta minus 20 degrees? Well, I'd still have to pull cosine 90 degrees to match it, but in that case, I would say sine of theta minus 20 degrees is equal to cosine of theta minus what, do you think?
It would be 110 degrees.
110 degrees, like that. All right. And then that gives you what you need to be able to think through those problems. All right. All right. So I'm gonna then get started with the lecture. And I think some of the questions that Noah, you were getting at with respect to problem 8, I think we'll get to here as we go. All right. So basically, we're going to be using, I don't want to say done complex numbers, but we're done all the new stuff we're going to learn about them. We're going to use them throughout the rest of the semester, basically from now until the semester is over, and they're used all the time in ECE problems. Okay, so we'll see quite a bit of them. I guess I should be updating the slides here. It doesn't say complex number introduction. These, by the way, these slides are uploaded to the Canvas page if you want to follow along directly in them. Okay. So essentially we've gone in, we talked about phasor, talked about complex numbers. Now we're going to kind of wrap things up and kind of talk through what's left. So these are the topics that we've covered, and I want to kind of summarize it a little bit. All right. So we talked about, I didn't change those intro slides here basically, but essentially what I wanted to do real quick is I wanted to summarize what we've done. Okay. We basically introduced 3 ways of looking at a complex number, right? The Cartesian or rectangular form, which is this one. All right. The complex exponential form and the polar form. As far as I'm concerned, these two are basically the same thing. All right. In fact, all the polar form is just a shorthand version of the complex form. And people seem to like this one better, the polar form, because it doesn't have e to the j anything, right? It seems friendlier. But, in general, I think this one is probably easier to remember because a lot of the rules we use, apply directly. All right, so the key thing about this, the relationships are summarized here. The real part of the complex number can be related to the magnitude and the cosine of the angle. The imaginary part can be related to the magnitude and the sine of the angle, right? And there we've got our other, kind of key relationships. One thing that we've talked about quite a bit, right, is if you want to get the angle, it's the arctangent of the imaginary part over the real part. And to be careful about this, the thing that we want to remember is arctan is only defined over here in 1 and 4. 1 and 4. Over in quadrants 2 and 3, arctan's not defined. So the recommendation I always have is sketch the complex number that you want to have, right? Look at that, figure out where it is, and then essentially if it's over in 2 and 3, add 180. Now I know you can get specific about whether you want to do minus 180 or plus 180. You're always going to get the right answer. What you may get is a negative angle or a positive angle. One thing to remember is that all angles, you can add 360 degrees to them or subtract 360 degrees from them and get an angle that's equivalent. Okay, we're going to talk about that more later today as we kind of wrap up from last time, right? So addition and subtraction are easiest in rectangular form. We've talked about that. Basically, you just add and subtract the real parts. You add and subtract the imaginary parts separately. So everything's just like vectors. All right. And then multiplication and division are easiest in the complex form because when you look at them, all you have is basically just exponential manipulation. All right. Which is something you should be familiar with. Okay. All right.
Professor?
Yeah.
I got a quick question. I know that arctangent is defined in quadrant 1 and 4, but I was seeing another class. It was saying like put the answer between negative 180 and 180. Why wouldn't it be like negative 90 to 90 or something?
Well, negative 90 to 90 wouldn't capture everything, right? Right. Negative 90 is here.
Mm-hmm.
90 is here. That leaves all of this area uncaptured, right?
Right, but I thought arctangent wouldn't be defined there, so you have to do some manipulation to get it over into 1 and 4.
You don't manipulate it to get it over there. You just say if you know that the vector is over in this quadrant, right?
Mm-hmm.
So let's say it's over here, and let's say I don't know, let's call this guy 2, 2 like that. So he's 2, so minus 2 plus J2.
Mm-hmm.
You'd say arctan of 2 over negative 2. If you do that, what you'll end up getting is negative 45 degrees. That can't possibly be right because that guy is over there. If I add to it 180, right, now I'm going to get 135 degrees. That's the right answer.
I see. Yeah, that's what I've been messing up.
Right. So basically, the problem that you run into is if, arctan, if it doesn't know whether I had a negative, if you think about it, I'm gonna get negative 1 inside here. It doesn't know if the negative 1 came from the top or the bottom.
Yeah,
And
no,
so
that makes a lot
it's
of
impossible to tell, right?
Yes, thank you.
Yep. All right. And then we talked about our two ways of examining a sine wave, right? So in general, we have this a cosine omega t plus phi. We use that because essentially what this does is it talks about how cosine is shifted from, so how a waveform is shifted from cosine, which is what happens in circuits, okay? Is that if we have a waveform that is sinusoidal or cosinusoidal and you put it into a circuit, the current and the voltages in the circuit are all just shifted from each other in some way, all right? And so this formula is kind of useful. And it allows us some simple ways to do things. And we're going to see more of that as we get into differential equations, right? And you'll see a lot more of that in circuits too. So we talked about this form, which uses Euler's notation, and then we talked about this form down here, all right? So you'll be expected to kind of know both of those on the test, that's for sure. And basically what I've got is we talk about, in this case, I got a forward moving vector and a backward moving vector. We've talked about that enough, which is that one vector rotates in the clockwise direction. That's the backward moving one. And the other one moves in the counterclockwise direction. That's the forward moving one. Okay? All right, now, this gets to the question that was asked at the very beginning. So the other thing we talked about here, we talked about this concept of the roots of a complex number, okay? The general idea here is that if I have some number a right here, so let's say this is 4e to the j 45 degrees. Okay, so this is about 45 degrees here. All right, what that says is if this is 45 degrees, we can represent that number multiple different ways, right? So another way of writing this is to say that it's 4e to the j 45 degrees plus what? How else could I write that?
360.
Yep, plus another 360. All right. And in general, I can say 360 times n, right? Where n is 0, 1, 2, so on and so forth. And in reality, I can actually define it even further, right? I could say -1, -2, right? It'd be perfectly fine to start talking about negative angles as well. All right. So what that said is, let's say, you know, I've got some relationship where I have x to the n equals some number, right? So let's go to a specific example here. All right. So x to the 5th plus 3e to the j 30. So if I have that, all right, I have x to the 5th equals -3 e to the j 30 degrees. Okay. So first thing about that is now I actually have two complex numbers multiplying each other. What's the magnitude of this guy on the side? What's his magnitude?
3.
3, not -3. All right. A lot of people want to start saying the magnitude is -3. -1 is a complex number, right? What complex number is -1?
A squared.
Not sure what you mean by that. What's?
J squared, he said, I think.
Yeah, I'm not sure what a squared means.
I think he was saying
J.
-1 is j squared.
Oh, j squared. Oh, yeah, which means that it's -1, right? But that's, so give it to me as just a complex number though, in either complex form or complex exponential form or in rectangular form. Right, rectangular form it's -1, right? Let's put that in complex.
Oh, you saying -1 plus j0?
Well, I mean, or it could be just e to the j 180.
Yeah. So yeah, I should be clear about that. So e to the -1 j0, or if I put that in complex exponential form, this is the thing that probably always throws everybody off. That's e to the j 180 degrees. Okay. Or -180 degrees. You can do either one. I wasn't very clear on what I was asking there. So does that make sense what I just did?
Yeah.
Okay. All right. 3e to the j 210 degrees. All right. All right. So now I've got, that's what x to the 5th equals to. So the way I look at this is, okay, well, let's just call this, I'm going to call that a. All right. So that tells me that x equals a to the 1/5. All right. And then I gotta find all the different roots. So I put in there that this is 3 to the 1/5 times e to the j 210, e to the j 210 degrees divided by 5, like that. All right, now that only gives me one root, right? So what we said last time is, well, I can use what we talked about over here, which is to say that the number basically repeats a bunch of times. All right, so the way that I do this, again, I'm going to go back into radians here for a second. I go back into radians only because that's MATLAB. Every trig function in MATLAB, and exponential is one of them, right? We've said this a couple of times, expects everything to be in radians. So what I'm going to do is I'm going to write this guy like so. I'm going to say that I have the angle here is, and I'm going to write this like so, 210 times pi over 180. That's the conversion to degree, or from degrees to radians, plus 2 pi n, all raised to the 1/5 power. All right. And this is true for n equals 0, 1, 2, 3, 4. Okay. All right. So essentially what I'm doing is I'm just taking 1/5 of all of the angles that I could possibly have. So 210, 210 plus 360, 210 plus 720, 210 plus 1080. So I'm basically just doing that for each of those. All right. Questions about that?
So that whole exponent is multiplied by 1/5 and 2/5 and 3/5 as you go on.
No. Where does it say that?
The 1/5 that you have at the end.
It's just
Of-
1/5. It's just 1/5. There's no n in there, right? This is an angle right here, right? I have that angle, and I'm multiplying that angle by 1/5.
Oh, okay. Okay. Yeah.
Right?
Yeah.
What's
So
what's going on is I'm changing the angle of this number. I'm basically saying, well, when n equals 0, this number is 210. So the angle would be 210 divided by 1/5. And then,
yeah. Okay.
then I'm adding 360 and taking 1/5 of that, right?
Yeah.
I think a lot of
okay.
people think it's multiplied, but you got to think about what's going on. What's going on here is that you're looking at equivalent angles, which means that you're adding, and that this number that you're multiplying by is only on this 2 pi component. It's not on the whole thing. Okay.
Okay. So you only multiply the 2 pi n part by 1/5, right?
No.
Or did I?
You multiply the whole thing by that, right? So
Okay. Okay. All right.
right. So, I mean, the simplest, I mean, one thing I think happens sometimes, you guys get too bogged down in the formulas, right? This is actually it's very easy to get bogged down in formulas. When you look at this stuff, you're like, what, e to the what? It gets very confusing very fast. But the reason I like to look at it this way, right, is if x equals a to the 1/5, right? If I think of it that way, if a is equal to 3 exponential of number, I don't know, I guess I shouldn't say a again, b like this, and I raise it to the 1/5 power, it's just 3 to the 1/5 e to the b over 5, like that, okay? And then what I'm doing for b is b can be 210 degrees, or it can be 210 plus 360 degrees, so on and so forth, right? So it's basically saying you do this for each of these choices, right? This idea hopefully should be pretty simple, right? This formula gets complicated, right? And it's easy to get bogged down in the formula, but if you think about what's happening just at a simple level, it becomes a lot more straightforward. Okay? Questions there?
Would now be a good time to talk about the MATLAB code for graphing this, in the notes that I asked about?
Almost. Let's go
Well,
to, so here for this particular one, I got my code. Okay. And let's use that as the reason to answer your question here. So if you look at, this is very similar code, right? So in this case, here's the formula that we got, all right, that we just worked out. And so what I did is I said, okay, as I looked at this, I have x to the 5th equals, I just left it as -3 e to the j 30 degrees. So I just left it that way. And I said n equals 5, right? So that's this guy's n. All right. And then essentially, when I look at this, right? So what am I doing here? So in this case, so let me first ask you, Noah, so in your question, do you understand how I'm doing the indexing here?
I see. So like you're inserting the whole function into because that's what A is, right? It's the whole function. So you're doing the absolute value of an entire function and then putting it to the power of n.
Well, no, I'm saying this is equal to A right here.
Mm-hmm.
And
I see. Yes. Okay.
And Noah, you have a good catch here. The important thing, I don't pay as much attention probably to the magnitude. I pay attention to the angle because that's really where you can make mistakes. And what there is a problem here in what I did. It should be that.
Okay. Okay.
All right. That
Uh,
that may not have been what you noticed, but that's definitely an issue,
no,
right?
yeah, that is one of the questions I asked about. But
Okay.
also I believe MATLAB took it still with like the homework took to the n, A to the n. Because I inserted it that way and I think it still took it. That's really where it confused me. Because I was like, if I look at it, it still took it. You know what I'm saying?
Yeah, that's okay. So your problem is that you got the right answer and you don't think you should have gotten the right answer.
Yes, yes. Because I was almost 100% sure that should have been 1 over n. And I understand now the angle A, now that you talk about,
Right.
Yeah, that makes sense.
Okay.
Yeah, that was the only thing that I had a question about. And I'll check.
Yeah, let me know that. I mean, at this late in the game, if I have a problem in that, I may just make that a free problem and give you the points for that, given it's that late. If there's a mistake in it, let me know if it, try it out. Let me know what you find.
So following the logic here, we just pushed everything over to the opposite side of x, then did some angle manipulation so that we subtracted a 180 from, or added, I should say, 180 to the angles in order to change the sign. So that
What I did, so I multiplied two complex numbers, right? I said I had -1 times 3 e to the j 30 degrees. That's a complex number multiplication.
right.
Right? So that's e to the j 180 times 3 e to the j 30. So that becomes 3 e to the j 210.
Okay, I
And then I just looked at that like if that was some number, and I raised it to the 1/5 power.
Okay, I understand then.
Right. And then, then because I need to get multiple answers, I do this basically for multiple equivalent angles.
I see. So it's 2 plus 2 pi times n. Well,
That's right.
for us, we'd have to make sure that the angle was in. I see. That's why the pi over 180 is there, to change it to radians.
Yeah. And, you could do this in degrees. There's nothing wrong with that. Okay. You could do this in degrees. The reason I did it in radians like this is because, as I've said before, the exponential function in MATLAB and all of the trig functions in MATLAB are done assuming that your argument is in radians.
Actually, if you just end the trig function in d, it assumes degrees. In d,
If you end the trig, you can do different things. Yeah, I don't. There's in MATLAB you learn that there's always 1,000 ways to solve a problem. I don't like sine d and cosine d, but you could do that. There are functions that they have different names, but they'll take degrees. Most of the time when I see people use that stuff, they use them wrong. I just say convert everything to radians when you plug them in. Okay. And Noah, you indicated, so the homework is correct. Okay.
Yes, sorry.
Okay. All right. Good. All right. Let's look at another problem like we did last time. We ran through pretty quick at the end, a problem like this one here. All right. So we said you know, one of the benefits of complex numbers is it allows us to simplify a lot of the math that we do, which again, isn't always all that obvious. We'll see it more as we go through the semester. All right. So let's say I give you this, integral e to the 3x sine 5x. And we're going to have integrals like this later when we get into things like Fourier series and stuff like that. We'll get into integrals that look like this. If I have this, one thing I'm going to say that we should be able to remember, let's anytime we got a problem like that, let's write out for ourselves this, e to the j 5x. If I use Euler's identity, how can I write e to the j 5x? What plus what?
Cosine 5 x plus j sine 5x.
Yep. So I can write it that way. So that tells me right there. Now if I look at that and I say, all right, well, let's multiply both sides by e to the 3x like that. All right. So if I multiply both sides to like that by e to the 3x, I could say that the imaginary part of that whole expression, so the imaginary part of e to the 3x times e to the j 5x, what must that be? What is the imaginary part of that?
E to the j 5x.
Nope. What's the imaginary part of that expression?
E to the j 5x.
E to the j 5x is not the imaginary part of that. E to the j 5x is a complex number.
Sine of 5x.
J sine 5x.
Not quite.
It's just the sine 5x.
So
That times e to the 3.
Yep. Okay. Yeah. So the j doesn't count, right? So the imaginary part is always the coefficient. So you basically have e to the 3x times sine 5x. All right. So the imaginary part is basically say when you look at the number in rectangular form, which part is the imaginary part? So which part is the coefficient on the j? So in this case, it's the e to the 3x sine 5x. So that tells me that I can write this integral as the imaginary part of integral e to the 3x e to the j 5x. All right, dx, like that. All right, you guys follow that? All right.
Yes.
All right, so now I'm going to say it would be the imaginary part of integral e to the 3 plus j 5 x dx, like that. Okay. All right. So in this case, it looks like I have an integral of e to the ax dx. What's the integral of e to the ax dx?
I just have a question. I know that it's cosine of 5x plus j sine of 5x. So why are we able to just turn the sine of 5x into e to the j 5x?
Because we're using the imaginary part. Notice we have it all in the big brackets that say imaginary. Because we have to convert that back
I
later.
see it. I see it. Thank you.
1 over
Yeah,
8 e to the 8.
basically what anytime we're doing this, I mean, what it comes down to is, calculus in this case, if I have exponentials and sines multiplied together, becomes a very tedious exercise. In this case, you do integration by parts, and you do integration by parts twice to get the answer, right? It would be a complicated process. However, what I've done is I've said, if I have sine waves like that, I can always recognize that the sine waves become either a real or an imaginary part. And so like you said, right, I still have the same integral. It just says I'm taking the imaginary part of this integral, which is going to have in it a sine term, okay?
Am I correct in saying that if we wanted to use the real part, it would be 5x minus 90?
5x minus 90.
Like if we were trying to like use the real part instead of imaginary.
No, the real part is just cosine 5x.
The real part would be the real part of this expression, right? So
Mhm.
e to the 3x times cosine 5x.
But wouldn't we have to? Okay, never mind. That makes sense.
Okay. All right. And I saw in the chat. So the integral e to the ax is 1 over a e to the ax. And I gotta be careful. It's an indefinite integral, so I gotta say plus a constant. Okay. So in this case, that just means what does that tell us for what this is? This guy has to be the imaginary part of what? What would our answer be here?
1 over 3 plus J5.
1 over 3 plus J5.
E
All right.
to the 3 plus J5.
Yeah, and at this point, I'm going to pull this out. I'm going to say e to the 3x times e to the j 5x. All right, and then I should say plus c. Okay. All right, so how would I get that? So first of all, your answer is never complex numbers. We give you a problem. If you started out with something that was, there's nothing imaginary about that. E to the 3x sine, it's totally real. Okay. There never better be any complex numbers, any j's in your result. Okay. So how do I get this back into something that is the right answer? If you'd done integration by parts, you wouldn't have complex numbers in it. So how would I get that back to an answer? All
You're
right.
saying turn it back into, I mean, when you say turn it back to a real, we're getting rid of the J, just keeping it in the form that we've now turned it into though, right?
Well, I got to get this. So basically, I got to expand this guy out somehow and get it into no COVID, allergy season. All right, 1 over 3 plus J5 times e to the 3x times e to the j 5x. All right. So I don't want to write that just straight in there. All right. E to the j 5x equals what? Well, how can I expand that using Euler?
Cosine 5x plus J sine 5x.
Cosine 5x plus j sine 5x. All right, like that. All right. So the way to then expand that is to basically say, well, again, one of the things I said I'm never really a big fan of here is doing division or multiplication when I have something in this form like this. But I'm going to do it anyway. If I'm dividing by a complex number, so I'm dividing by 3 plus J5, what do I do? How do I have to deal with that?
Multiply by the conjugate.
Yeah, and I got to be careful. I got to multiply top and bottom by the conjugate.
Oh, sorry, yes.
Yeah, like that. All right. And I honestly hate this process. There's a better way to do it, but you should know how to do this as well. So when I do this, what do I get on the bottom? What's the bottom become, the denominator? Anybody know what's gonna come from that?
Wouldn't it just be 1?
Nope.
Plus 20.
So if I take 3 plus J5 times 3 minus J5, so I multiply a number by its conjugate, right? What you'll find is that the imaginary parts go away. Yeah, I see someone writing 9 plus 25. I get 9 plus 25, which is 34, right? There's no imaginary part to that, all right? And so that's one nice thing about it, all right? Then I get e to the 3x. So this guy is entirely real. Everything there is real, okay? Then I have 3 minus j5 times cosine 5x plus j sine 5x. And looks like I then need to multiply those two things together, right? So if I multiply all that stuff together, one of the things that I recognize, all right, is there's going to be e to the 3x over 34 times, let's just focus on which parts are going to be imaginary. When I multiply this out, all right, which parts are going to be imaginary? So this is a foiling process, right? So I get what? Minus j5 times cosine 5x. What happens when I multiply minus j5 by plus j sine 5x?
Turns into a real.
Turns into a real, right?
Sine 5x.
Yeah. So I'm actually I'm going to ignore it in the end because I know that I don't need it as part of the imaginary part. Where else? There's another multiplication that'll give me an imaginary part, right? How about 3 times j sine 5x? So j 3 sine 5x, like that, right? So there's also a real part term, right? So if I looked at this, there's a real part term. What would it be? It'd be plus 3 cosine 5x. Let me do that. And minus j5 times j is going to be plus 5 sine 5x. Okay. So that whole thing, these guys are the real parts. This is the imaginary part. So if you look at what my final answer is, here's my final answer. Okay. So what that tells me, and sorry, that should be the imaginary part. This is the imaginary part. Oops. All right. You guys follow what I did there?
Yeah.
Okay. All right.
100%. Hold on. I thought that, no, I understood the math as we followed through it with the divisions and things, but I thought we were taking the imaginary and only the imaginary portion because that's the only part of it that we had.
That's the only part that we care about. Okay. So what we said at the very beginning of the problem is that I took this I took this integral and I realized that the thing I'm integrating, the integrand, e to the 3x sine 5x, is the imaginary part of e to the 3x times e to the j5x. So what that says is I can compute the integral of this complex thing and then take the imaginary part of whatever the result is.
Understood.
Okay. And so what I did was I said, all right, well, if I do this integral, what I get is this result. All right. And then at the end of all of it, I need to take the imaginary part of both sides. Like that. Okay. And so I go through and I carry out that process. So what I'm doing here is I'm just looking at this result by itself here for a second. And I'm expanding it out. And at the end of the day, what I do is I just simply take the imaginary part, which is only these terms right there. Or at least only the coefficients on these terms.
Oh, okay, I understand now.
Right? And so that's why here in the final answer, I mean, technically it's this, this times j, and I take the imaginary part and the j goes away and I just get that. Okay?
Okay.
All right. So the other way of looking at that, and actually the way that I think is easier, is what I did here. All right. So what I did here is I'm saying, well, I have this complex number 1 over 3 plus j5, okay? To me, I could say that that is a complex number with that magnitude, okay? So how did I get that magnitude right there? How did I get that magnitude?
Squared plus 5 squared, square root.
Yep, 3 squared plus 5 squared, square rooted. And then I say this guy has an angle of what? What would be the angle of this as a complex number? How would I get that?
Tangent 5 over 3.
5 over 3.
So arctan of 5 over 3 is the angle of the number on the bottom. So I'll do this maybe slowly here. So I can write this guy as this. Tan inverse of 5 over 3, like that.
To get that on top, we can make it a negative exponent.
Yep, and to bring it on top, because on top, right, basically I got e to the 0. So e to the 0 divided by this gives me 1 over square root of 34 times e to the negative j tan inverse 5/3, like that, okay? And so that's what I have right here, okay? Now, why do I like that better? Because when I look at this thing right here, if I say take the imaginary part of that, the way that I look at that, pretty simply is to say this guy looks like to me, all right, this guy looks like it's e to the j theta times e to the 3x, where theta is equal to j5x minus j arctan of 5/3, which if you compute what that is, right, this guy is 59.04 degrees, okay? So reason I like that, to me, it seems like it's fewer steps, right? And again, I prefer to do that when it's fewer steps for one reason. But in general, I think, this kind of idea of I'm getting phase shifts turns out to be much more useful than creating some expression with multiple sines and cosines. What this ultimately says is this expression has to be equal to this expression. If you plotted those versus x, they would look exactly the same, okay? We're gonna deal with that later, all right? But this is usually a harder way to think of things in this form than this is, but they're entirely equivalent to each other, okay? And then, I went about just shifting it over to, a cosine just to show that I could, and to see if anybody had any questions about that. All right. You guys follow what I did there?
Yep.
Not precisely. I kind of get it.
Well, I mean, this is one of those things that, I think practice is the key thing, right? What I'm really doing is I'm just taking a different approach, and I'm just saying, all right, if I have division, which is what I have here, right? I have this complex number, this complex number here is being divided by 3 plus j5. So if I'm dividing, then instead of keeping it rectangular, I make it into complex exponential form or polar form, and then I'm just subtracting their angles. All right, that's all I end up doing here, and then I end up taking the imaginary part of the result. Okay. It's one of those things you just gotta do it and practice it, and that's how it kind of comes to you. More questions there?
Just confirming, because it's imaginary, it's equal to, you just take the j out. That's what it looks like, right? Like, the j is no longer there because it's imaginary.
So, all right. So the term real and imaginary in that context, right? So if I told you I had,
Wait, I see what you're using Euler's, right?
I am. Yeah. Anytime I take the
Yeah.
imaginary part of something, so if you expanded this out, right? Think of this as e to the 3x times e to the j theta, where theta is this, right?
Yeah.
And then
Yeah,
what I did was
understand.
yeah, okay, 1 over square root
Yeah.
of 34 times cosine theta plus j sine theta, all
Yeah.
times e to the 3x, right? So think of it like this. If I say imaginary part or real part, right? What that kind of comes down to is if I had a vector 3x hat plus 4y hat, and I said to you, what was the x component? You would say 3. What's the y component? You would say 4. Think of j in that context as being like those unit vectors you saw in physics, right? That's probably one way to think of it.
Okay.
All right.
But in this case, J actually means something.
Kind of, yeah. It does and it doesn't. I don't know.
Alrighty.
That's a tricky question. Yeah, it does. It means it means it has an angle.
Yeah, that's why I consider it something, but I don't want to consider it something if I shouldn't, you know?
It's a tricky concept, but you know, it basically means a rotation, right? So it means that some number is rotated 90 degrees from where it would be otherwise, right? But the imaginary component is always just the coefficient on the j.
Now, real quick, how did we get 59.04 degrees from j5 of x minus j tangent of negative? Or did we just convert that? Hold on.
So I got it from this, arctan of 5/3. Because notice, you know, the 5x here,
Oh,
this
no, I
is a
understand
frequency
now.
term.
Arctan of 5/3 is 59.04. That makes sense. I'm sorry.
Right. Okay. Yeah, it'll be, you know, again, this is kind of thing we're going to get used to over time. All right. So the other thing we did the other day, right, is we went through and we looked at how to expand this guy using Euler's identity. And you have some of this on problem 9 as well, okay? So what we said is if I have sine of theta or cosine of theta, those things can be expanded in terms of 2 exponentials. So let's do cosine theta first. How can I expand cosine theta? What plus what? I got a 1/2.
If you want, wouldn't it be 1/2 times e to the
J theta
J theta. Yep.
plus
e to the negative J
1/2?
theta.
Yep. All right. And it's very similar when I'm in the sine. It's 1 over 2j e to the j theta.
Minus 1 over 2j e to the negative j theta.
Yep. E to the negative j theta. Okay, like that. All right. So I can use that here and I can say, well, that means that this has to be 1/2 times 1 over j. So 1 over 2j e to the j 3x plus, or sorry, minus, this is a sine, e to the minus j 3x. That's the sine term, okay? Then for the cosine term, I say times 1/2 e to the j 4x plus e to the minus j 4x, like that. You guys follow that? All right, just a straight up substitution, right? Now what I got to do is turn this into 1 over 4j, and then I do essentially a foiling operation. All right. Now we did that the other day, and so when I say foiling, what that means is I take e to the j 3x and multiply it by e to the j 4x, and e to the j 3x and multiply it by e to the negative j 4x. So that gives me e to the j 7x. And then what happens when I multiply e to the j 3x times e to the minus j 4x? What's that become? E to the what?
E to the
Minus
negative jx.
J7x.
Yep, minus jx. And then I got to do the foiling this way, right? I got to multiply the second term by both of these guys. And that becomes what? Minus e to the jx minus e to the minus j7x, like that. And then what I did last time is I grouped the terms, right? I basically said I got 1 over 4j times e to the j 7x minus e to the minus j 7x. And I also did this, minus 1 over 4j times e to the jx minus e to the minus jx. All right, and I grouped them that way on purpose. Why?
Because one's for the sine and one's for the cosine.
Yeah, so what does this look like? If I do some pattern matching here, right, e to the j, this looks like I have a 1 over 4j times e to the j theta minus e to the minus j theta. Like that, right? What do I turn that into?
Sine, the
That's
sine
a
of theta.
sine. Yep, and I got to be careful. That's actually 1/2 sine theta. Sorry, guys.
So that step where you separated, that's a requirement, correct?
Well, it's a requirement only in that if I'm trying to identify the terms here,
Okay.
that becomes an issue. Now you guys are going to think I have COVID.
We already do.
All right. All right. So when you look at this, okay, so then how do I break this up then? I'm going to say I got 1/2 sine of 7x. Sorry. Minus 1/2 sine x, like that. Now, that ultimately, the reason, the context in which I give this to you in the homework is I give you an integral of like sine 3x, cosine 4x, like that. And when you do that, it becomes really hard to do. All right. The integral of these guys is much easier. All right. I say hard in the context of it takes, it takes the, it takes the, you guys are funny. All right. When I take, if I say, the reason I say this integral will be hard is because I have to do that integration by parts. All right. Integral e to the j 7x, like that, dx. If you did that integral, it becomes a lot easier. 1 over j7 times e to the j 7x, like that. All right. All right. The other thing you can do is you could somehow convert that over into a cosine or sine. You could do some different stuff with that. I'm not going to focus on that, really. What I wanted to talk about real quick, just here at the end, is just a little bit of a note about plotting in MATLAB. Okay, so if the whole idea, sometimes you go into your calculator. If you say I had a function, right, f of t, right, f of t equals, I don't know, cosine of 30t, right? You can tell your calculator, put in cosine 30t, and it draws a graph of that. And it makes decisions about the time vector for you. Anytime I'm in a computer, the problem I have is I have to tell the computer at what points to evaluate the function. So basically what you're doing every time you do any kind of plotting, you're creating a vector of points. And you're saying, okay, take that function and evaluate that function at those points and get this corresponding vector, right, that's computed at those points. So if t equals, that's a bad t. If t equals 0, 0.01, 0.02, so on and so forth, then this guy becomes cosine of 0, cosine of 0.01, and so on and so forth, right? Like that. So it's one thing to bear in mind, right? So anytime I'm computing a vector, the whole reason I have to create this time vector and then compute it is because there's finite memory in the computer, right? It can't deal with time being infinitely precise, right? And so we have to just choose the times at which we want to do it. So that creates an issue when you got something like what you have in number 7 in the homework. All right. And I introduced that one because, well, it's more plotting, but it also introduces you to a little bit more stuff that you kind of know about already, which is if statements, right? You've seen that in C. And so we wanted to look at how they were implemented here. Okay. And that's there in the homework. I posted an example which actually covers this one. And in that example, what I talk about is, okay, for t less than 0, I see that this function, all right, I'm going to write it like this. I'm going to call this function v of t, because apparently I said it was a voltage. V of t, if I write it out like this, is 0 for t less than 0. It's some linear function, a t plus b, for t between 0 and 2. And then apparently for t greater than or equal to 2, it's 0 again. All right, so I go through this example in here, right, in a video, but I wanted to kind of talk about this real quick. So so to do this, hopefully you can see where an if statement is kind of a natural way for me to do this. All right. In MATLAB, I basically, the way I'm going to do this, I wrote a for loop, and I wanted to just take a quick look at it. All right. Before I do it, I guess if you look at this, an if statement would work. All right. MATLAB has if, else if, and else, like that. All right. So if, else if, and else. So for each of those, you got to have some kind of what we call logical or relational test to know whether or not your code should enter these, sort of different areas. So in this case, if I have an if statement like this, right? How many regions do I have to define here? How many things do I have to check? How many if, else, how many of those things do I need?
3.
Yeah, I could do it with 3. Turns out I could do it with 2, right? But I could do it with 3. Let's say I do it with 3, right? I could say, in this case, I could say, well, if t is less than 0, all right, then v of t is equal to 0. Else if, I could say if t is, now how would I write, what would be the else if I did it like this?
Could you do t less than 2?
Yep. If it's in this range, right, then I want v of t to be equal to a t plus b. Else, I don't need to define anything for an else. Else, just the only thing it could be is that t is greater than 2 and it's equal to 0. All right. Now I wrote that out in sort of pseudocode. I didn't write that out in sort of MATLAB code. All right. What's the problem with this? Could I write this in MATLAB? Would this work?
Maybe, but my concern is the if and the if for the 0. I don't know because if t is less than 0, it's going to read the if and then go to the if else and possibly read that one as well.
You mean at t equal to 0?
Yes, or less than, because it goes if t less than 0,
yeah,
and then if else 0 is, or t is still less than 0.
No, right? So so the boundaries we've got are perfectly fine. Those boundaries, there's no issues with that. I mean, at t equal to 0, it'd be a little bit awkward potentially, but it's not turns out to not be a big deal. The bigger issue is if I defined a t vector here, and I defined a voltage vector, right? T vector just has some numbers. So let's say I do it from -4 in steps of 0.01 up to 4, like that. And I started out with a v vector equal to just nothing. This would be problematic in MATLAB code. What would I have to include with this to be able to make this work? I'd have to have some kind of a loop to go with this, right?
And I guess a counter for the vectors.
Right. So what I would have to do with this, right, is I would have to go through and do some kind of a for loop here. All right. I have to some way to loop through this guy. If t is less than 0, I can't do an operation on a whole vector like this. Okay. And so what I got to do is I got to check each individual value for each each point in this time vector. I have to calculate a separate value in this v vector. All right. And so the way that I wrote this, all right, in the code that I talked about, and I'm going to come back to the other slide before we finish here. All right. The way that I did this is I basically looped through the t vector. All right. So I started from, so I said for n equal to 1, I call this thing here an index. Oops. All right. This guy is an index. And he basically is just some variable that lets me know where I am in a vector, right? So I say for t, if the value, so think about what's going to happen. If you think about the way this guy executes, initially he's going to set n equal to 1, and then he's going to check to see, well, if t of 1 is greater than or equal to 0, and the ampersand means and t of 1 is also less than or equal to 2, then x of n should be equal to this value. So it basically says x of 1 would be equal to that value. Now, t of 1 is over here, right, at 4. So it would go to the else statement, and it would say x of 1 is equal to 0. And it would keep incrementing until eventually n was high enough that my time vector was in this range, okay? So basically what I'm doing is I'm computing individual points in that vector, and then when I'm done, I'm making a plot of the whole thing, all right? One thing, if you ever want to understand and kind of follow what your loop is doing, one thing I would say is you could always, in MATLAB, easily output stuff to the screen. You could say, well, just write n like that. And then it'll tell you what the n value is. And then maybe don't put this colon here, and don't put this colon here. And then I can watch x and n as time evolves. And that'll give me some idea as to how the code is functioning. Okay, and I can do a little bit of debugging with that. All right. And we can talk a little bit more about some debugging techniques if you guys want to talk about that. We don't have a whole lot of time to do it now, but we could certainly do so in the future. All right. All right. Now, one thing I linked to this in the on the Canvas page. It's in the book. But essentially, when I look at my relational operators and my logical operators, right, when I'm looking to see if two things are equal, I put equal, equal, right? When I have not equal, this guy didn't come out that clearly, but it's the little tilde, all right, is what not equal to means, okay? And so that tilde is usually next to the 1 key on your computer, okay? All right, any questions about that stuff? Got to be at least one question out there.
I have a question that doesn't necessarily pertain to like this logical and like the problem 7 in terms of homework, but for problem 9, this is going back a little bit. When after we get through the integrand and stuff like that, and it comes to graphing, you want us to set the constant of integration to 0?
Yeah.
So basically, we're just graphing the function after it's been integrated, right?
That's right. Yeah.
Okay. Just making sure. I was like, it was late last night. Anyways, thank you.
Yep. All right. So I guess I'm gonna go ahead and stop there.